Well, aloha, everyone. Today, we are going to be talking about the magnetic field of a wire.
Last time, we talked about how moving charged particles.
Create magnetic fields.
So I've set up a little experiment. We have a power supply. Out of the power supply, from the positive side, there's going to be current that runs through this wire. It's going to go down through this wire to this ammeter and then back around to the power supply. That's the circuit. As part of this experiment, I have placed, this is just a paper plate that I have. I poked a hole through it and ran the wire through it. And around this, I have some miniature compasses that I have placed around the wire, like so. Watch what happens when I turn the current on. So when the power is off, all the compasses are aligned in the same direction because they're pointing north. They're all aligned sort of that way, and north happens to be pretty much that way. But when we put power through this wire, when we put current through this wire, they all line up kind of in a circle around it. Watch again carefully and see if you can see that. So that means that this wire is creating a magnetic field that is stronger than the Earth's magnetic fields very close to it. As you go farther and farther out, the magnetic field of this wire gets weaker. And how do we figure out the direction that the magnetic field is pointing? Well, it turns out we have something called the second right-hand rule. Here's how it works. You take your thumb and you imagine that you are grabbing the wire with your thumb pointing in the direction the current is flowing. So in this section of the wire, current is flowing down through the paper plate. So I imagine I'm grabbing this wire with my thumb pointing that way. This means that there is a magnetic field wrapping around this wire in the same direction my fingers wrap around it. So the magnetic field of this wire is pointing in a circle around this way.
So let's imagine that we have a wire. Our wire is horizontal like this. And first of all, the wire itself does not generate a significant magnetic field, at least when it's sitting there on its own. We need to put electrical current through the wire. We need to have moving charges for this wire to start to generate a magnetic field. So what does that mean? Well, let's say we put some current into it that is directed that way. So what we're going to do is we're going to take our thumb and we are going to line it up with the direction of the current. For me, that's that way, though I think the camera reverses things and looks a little bit weird on camera. But for me, it's this way. If I was to grab this wire, I could then easily see that the magnetic field of this wire is going to wrap around it in a sort of I don't know what you call it, but in concentric circles, kind of going this way. So that means on the top of this wire, the magnetic field will be directed out of the page. In the bottom of this wire, the magnetic field will be directed into the page. And remember that this isn't just, this is a 3D view of this. So if we were to look at this from the end, let's say that we came over here and we're looking at it from this side, our view would be a little bit different. So as I look at this from that end, if we rotate this whole thing, we can see that this magnetic field would be, I think it'd be pointed this way on top, that way on bottom. It'd be going this way on that side and this way on that side because we have current going into the page. So you can see that we would get this sort of, if we were to draw the full magnetic field instead of just sort of parts, we'd get this, that wasn't very good. we'd get this kind of loop thing that would be directed in a circle around in that direction. So we're going to find magnetic field lines in circles around wires, and it's going to look sort of like this. So this is from our view originally on the left, and on the right would be if we're looking at it on end from right there. So we know how to calculate the direction of the magnetic field based on the second right-hand rule. But the problem is we still need to figure out how strong that magnetic field is going to be. So what is the strength of the magnetic field? Well, there's a few things that's going to affect it. The magnetic field strength is obviously, it's going to be a vector because it has a direction. And I'm going to put the absolute value signs or the magnitude signs around this because this formula is going to tell us how strong it is at any given point. Now, obviously, it's going to get stronger if you have more current. The more current you have flowing through this wire, the stronger the magnetic field will be because there are more charged particles moving. So, obviously, the current is going to be an important piece of this. Likewise, the farther you get away from this wire, the weaker the magnetic field is going to be. So it's going to be inversely proportional to the distance from the wire. We're going to call that R. And then there's going to be one more piece to this formula. It is going to be a physical constant that has to do with magnetic fields. It's going to be mu naught over 2 pi. The idea behind this, we see that there's a 2 pi in there. It sort of makes sense because we have this circular thing going on. And the mu naught is going to be a measurement of, you can think of it, it's called actually the permeability of free space. And it's a universal constant that you can think of as how hard it is for a magnetic field to go through empty space. That's sort of what it measures. I obviously is current, and R is the distance from the wire. The permeability of free space, mu naught, is going to be equal to 4 pi times 10 to the negative 7th. And then there's these kind of weird units on it. It is going to be Tesla meters per amp. And you'll see it works out, but just kind of crazy units on that. Okay, so let's imagine that we had a current of 4 amps flowing in this wire, and we were a distance of, let's call that, I don't know, 0.2 meters away. So R is going to be 0.2 meters. We're going to talk about a point somewhere up here, 0.2 meters. There we go. And we're going to talk about the current is 4 amps. So what is the strength of the magnetic field at that point? Well, B is going to be equal to mu naught over 2 pi times I over R. That's equal to 4 pi times 10 to the negative 7 Tesla meters per amp over 2 pi times a current of 4 amps divided by a R of 0.2 meters. And let's see here. Let's start off by looking at units before we solve the numbers here. We have an amps on top here, amps on bottom there. We have meters on top there, meters on bottom there. And we can see that the unit for a magnetic field is going to be Teslas. Let's see what number we get. When I do this, I get 4 times 10 to the negative 6 Teslas. So it's a pretty weak amount of magnetic field from this one wire. But also remember, a Tesla is a very large unit of magnetic field. In fact, we're talking about like an MRI machine, which has an incredibly powerful magnetic field. We're talking about 4, maybe 5 Teslas. So a Tesla is a huge amount of magnetic field. It's enough to make, keys get ripped out of your pants or pieces of metal go flying across the room. So if ever you have an MRI, they make sure that you have no magnetic ferromagnetic materials on you, because really bad things can happen if you do.
Now, the magnetic field of this wire isn't strong enough to do something like affect a paperclip just yet. If I turn this current on, I really don't feel anything. You'd need a pretty big amount of current in order to start noticing any effects. But there's a way we can enhance this. First, by using a longer piece of wire, I'm able to get more turns on my electromagnet that I'm building here. Second, you'll notice I have wrapped this around a metal rod. This rod is made out of probably stainless steel, but some sort of iron alloy. And since we know iron is ferromagnetic, we know it will enhance the magnetic field that this wire is creating. So right now, nothing. But if I give this magnet some current, you will see it immediately becomes magnetic, and it's able to pick up paper clips. If I turn it off, the magnets come off, but there is actually a little bit of residual magnetism that will remain after I turn it off sometimes. And so sometimes you'll see one of these will just barely stick a little bit, even after the power supply is off. We think natural magnets, often called lodestones, have a similar property. When lightning strikes the ground near some magnetite, it may magnetize it for a while, and that residual magnetism stays around and creates a permanent magnet.
So why does winding this into a coil make the magnetic field stronger? Well, you can think about it like this. Imagine you have a wire carrying current this way. And now the current goes around the back, and then it comes back in another wire going this way. And then you come around in another wire going this way. Well, the magnetic fields of all three of these wires, let's say at a point down here, we can use the second right-hand rule again. We can grab that wire and we can see that it's going to be into the page down here. And out of the page up here. So as that current builds up, as you get more and more turns, you get more and more magnetic fields from each of these wires. You can pretend that you have a whole bunch of wires that are independent of each other, all carrying the same amount of current, all in the same direction. Because of that, each time you have current flowing, you're going to get a reinforcing effect on this magnetic field. If you have this wrapped around 100 times, the magnetic field would be 100 times stronger than it would be from a single wire. So that's really all there is to it for the magnetic fields due to a wire. So, mahalo for watching, and see you next time.